So let's start Lecture 3, Part 7, which corresponds to Section 3.7 of your text. And the nature of this section is Lecture 3, Part 7. We're going to be talking about applications of derivatives. So the first 6 sections of Chapter 3 dealt a lot with the theoretic computations of derivatives of many types of functions. And so now we're going to take those computations and we're going to put them into a context of solving different types of problems, applications. So in this case, Section 3.7 treats the subject of rates of change in natural and social sciences. So as the words imply, rates of change. We're going to be looking at how some phenomena from, say, physics or chemistry or economics or population growth, each of these are characterized by a time rate of change of some phenomena in those disciplines. Okay, so before we commence, just take a quick cursory review of things that we should know. So again, we're going to compare and contrast the distinction between delta y over delta x versus differential y over differential x. Okay, so here in this illustration, I've got some hypothetical function y equals f of x drawn, and you can see its outline in blue. And at the points P and Q, okay, are on the function. And P, of course, is the abscissa. P evidently is x sub 1 on this graph. And what we're going to do is we're going to start off by say, let's draw a secant line connecting P and Q. So shown in green is my secant line. And of course, delta y over delta x is the slope of the secant line shown in green. So what we have is delta x is being right here. We have x sub 1, and then the abscissa of Q would be x sub 1 plus delta x, and that's essentially our x sub 2. So x sub 2, for all intents and purposes, is x sub 1 plus delta x. Okay, so that's x sub 2, and so you can see the secant line has a particular slope. So what we do by construction is we go to point Q, and we drop a perpendicular from Q to the x-axis. Okay, and where the perpendicular intersects the x-axis, that's our definition of x sub 2, right here. And then we'll take this. Okay, and then next what we do is we go to point P, and we consider point P the point of tangency for the tangent line to F at P, and that's shown in red. So you can see the red line, and so point R is, okay, the way we produce point R is we take this perpendicular from Q to the x-axis, and we just extend it, continue to extend it indefinitely until it junctions the tangential line. And so we have the intersecting point of the tangent line and this perpendicular to be called point R. Okay, so now, as we know, differential x is the distance. Oh, okay, well, all right, so I need to define what point S is. So point S is this line segment drawn parallel to the x-axis through P, the point of tangency. And where this parallel line junctions this perpendicular, we call that point S. Okay, so differential x is x1 plus delta x minus x1 for very small delta x. So differential x is the same as delta x. Okay, so that would be the run, so to speak. Now, delta y, of course, is the change in height as we ascend from P to Q on the function. Okay, and so delta y. But now differential y, okay, that's a different story. It's the distance from R to S. Okay, so it's the difference from the ordinate of R minus the ordinate of P. Okay, so it's essentially defines the incremental change in y with respect to an incremental change in x for the tangent line. So differential y over differential x is the slope of the tangent line, and delta y over delta x is the slope of the secant line. And you can tell that differential y is not the same as delta y, okay, just by through the picture. And so the slope of a tangent line is not necessarily the slope of the secant line. Of course, if we drive the slope of the secant, if we drive delta x in the computation of the slope of the secant line towards 0, then of course the slope of the secant line will converge toward the slope of the tangent line. So we make use of this fact in the word problems. Okay, if we hold on to this thought, we can get through the word problems here. So again, just for clarification, MPQ, okay, M subscript PQ is may be considered as the average rate of change. And I think many of you have gone through the WebAssign problems already and have worked through these types of problems. And then F prime at x sub 1 is the instantaneous rate of change. Okay, so we have two classifications of rates of change. We have average and instantaneous. And we'll be comparing and contrasting the two as we go through the problems. So the first class of problem we'll deal with is something from physics. We'll deal with particle motion from physics. All right, so we have an illustration here. We say let's let S equal to a position. Okay, so S is a position function with time. So go ahead and make it a position function. And we'll say that that equals to T cubed minus 6t squared plus 9t. All right, so we have this particle motion with respect to time, and this is the position of a particle with respect to some reference frame. All right, and so if we were to graph the position as a function of time, let me pull up an illustration of what that would look like. Let me extract the drawing. So the graph of this function would look something like this. Okay. All right, so it's kind of a little bit on the blurry side, but this is the, here we have the t-axis. Okay, and then here we have position as a t. All right, so that's the graph. Now, we have also velocity. So we want to know the velocity of the particle at different times. So recall that the velocity is the change in position with respect to time. And so here we have instantaneous velocity because we're using differentials. Okay, so this would be your instantaneous velocity. And then of course you can take the derivative of the position function. So that would be 3t squared minus 12t plus 9. All right, so we have the velocity, instantaneous velocity at any time t. So now, a couple of questions. When is the particle at rest? Okay, so when is the particle? When is, okay, yeah, so when is the particle at rest? When is the particle the keyboard out of the way? All right, well that obviously happens when v of t is equal to 0. Okay, so all we have to do is solve this equation. So 3 times t squared minus 4t plus 3 is equal to 0. So we can factor this, right? Looks like it sets it up for factoring. So we have t minus 3 times t minus 1 is equal to 0. So the particle is at rest at t equals 3, and that's my symbol for and. T equals 1 seconds, okay? So at those 2 times, the particle is at rest. What else? Okay, when is the velocity of the particle less than 0? In other words, essentially a negative velocity. It's going, I guess, backwards, right? Okay, so we can answer this question. When is dt less than 0? And when is dt greater than 0? Okay, well, the way we can answer that question is we can just assemble a table of signs. So we know the velocity function has 2 factors. So using our table of signs, okay. All right, so we have 1 and 3, and they're both in the domain of the velocity function. So when t is less than 1, that's a negative factor, so plus there. Okay, when t is greater than 1, that's a plus there, minus there, so we have a minus there. So the velocity is less than 0 between 1 and 3, and the velocity, of course, is greater than 0. T greater than 0. And that makes sense, okay? Because look at our position function. Now we know that the velocity are the sequence of tangents to the position function, okay? And we know right here we transition from, at this value of t, which is what, t equals 1? See, t equals 1, which we said when the velocity is 0, we transition from an increasing velocity to a negative velocity, okay? Ostensibly, we're slowing down, perhaps, okay? And you see the negative tangentials mean a negative velocity. And then here at 3, we have a transition from negative to positive, so right here. So just looking at the graph, it makes sense, and it confirms the accuracy of this table of signs. And then, of course, we have acceleration of the particle. So acceleration is a function of time. That's the change in velocity with respect to time. And so that would equal to what? Well, here's our velocity function, so that would be 6t minus 12. 6t minus 12. And I guess that would be what? Perhaps something like in centimeters per second squared. I don't know, whatever the units are. It's a unitless value for the time being. All right. Okay. So we can talk about the total distance the particle travels on an interval. So total distance okay. So from 0 to 1, so we have the total distance from 0 to 1, and say from 1 to 3, and then say from 3 to 5. So the total distance during these time intervals. So rate velocity times time is equal to 0, right? So we can calculate those. So I think we'll need more tools to calculate that, and that'll probably come about in Chapter 5. But what's interesting about this particular problem is we have a couple of categories of the notion of when the particle speeds up. So take note of this. The particle speeds up to u when v is greater than 0. and v is increasing. Okay, so v is increasing. In other words, the acceleration is positive. One second, I want to check something in the book. Let me pull the book. There's a technical note I see, maybe an omission in the book. Make sure it's covered in this lecture. So let me turn to section 3.7. Check something in the text. Make sure the author got it right, because sometimes his notions of physics aren't always correct. Okay, yeah, so we can answer that. We can answer the distance traveled. Yeah, I think we can go ahead and do that. Okay, so I'll do that. I'll answer that question as well. Okay, so distance traveled. Okay, all right, so the particle speeds up when velocity is greater than 0 and v is increasing. So what this means is, this means both velocity and acceleration are greater than 0. Okay? Also, the particle, so here's what a lot of students get mixed up with. The particle is also speeding up when v is less than 0 and v is decreasing. Okay, in other words, there's a force acting on the particle which is causing it to decelerate and go in the other direction. Okay, so that means if it's decelerating in the opposite direction, it has to be accelerating in the forward direction. Okay, so that means that v is decreasing. So we have these two conditions for a speeding up consideration. All right, so make sure you understand these. Okay, two conditions. All right, so now, do we have some questions here? All right, so let's see here. So we want to answer all of these questions. The total distance from 0 to 1, 1 to 3, and 3 to 5, and on what intervals is the particle speeding up and slowing down? All right, so let's answer the question, the first question, the distance traveled in the first second. So the distance traveled in the first second would be the position at 1 minus the position at 0. And we take the absolute value because the particle can go forwards and backwards. And so all we're interested in is a distance, which is the absolute value of the final position minus the initial position. Okay, so final position, s at 1, minus initial position. We subtract those two quantities and we take the absolute value for distance. Okay, so that's just distance. Distance is just a number. It doesn't tell you which direction. So we have s at 1, if you plug it into the position function, is 4. And of course, the initial position is 0, so we'll say 4 centimeters or something like that. All right, so that's the distance traveled. Now from t to 1, okay, so the distance traveled from t to 1 would be the position at 3 minus the position at 1. Okay, and so that would equal to, now the position at 3, of course, we've already deduced that that's 0, and the position at 1 is 4. So again, 4 centimeters. Okay, even though it went seemingly backwards, it did travel 4 centimeters. And then from 3 to 5, the distance traveled from 3 to 5, so that would be the position at 5 minus the position at 3, absolute value. And so the position at 5 is 20 when you plug in t equals 5 into the position function. And then we know that t equals 3. At t equals 3, the position is 0, so 20 centimeters. That's the distance traveled. So the total distance would be the sum of these three quantities. Even though it traveled backwards and forwards, it still traveled a distance. You have to add up all of the distances it traversed, even though it was going backwards and forwards. It may not have, so as opposed to displacement, where its final position would be its displacement. So its displacement may not be the total distance traveled because of the fact that it's going backwards and forwards. So this would be 28 centimeters. All right, so between 0 and 5 seconds, this thing traveled 28 centimeters. Okay, so we have that. All right. Okay. So let's see what else we can answer about this. Oh yeah, and then the next question, of course, is where is the particle speeding up and slowing down? Okay, so let's figure that out. Okay. Okay, so that would happen. We need a graph, right? So we would have to plot acceleration and velocity on the same graph. So let's grab that. Let me see if I can pull that off. Okay, so bear with me while I pull up the drawing. Okay, so let me grab the image. All right. So let's see what we got here from the notes. Okay, so in this illustration, what I'm showing is the velocity is shown as this parabolic trajectory. This is the parabolic velocity. And the acceleration curve is shown in black, but I'll accentuate it in green. So this is what? This is 6t minus 12. This is your acceleration curve. Okay, so now, so we said that, okay, so what was the question to see where, on what time intervals the particle speeds up and is slowing down? Okay, so, okay, so now consider the interval 0 to 1. Okay, now in this case, from 0 to 1, here's how you interpret the information on this graph. From 0 to 1, v of t is above the x-axis. Okay? You see that from 0 to 1? And from 0 to 1, if we were to continue on with the graph of the acceleration graph, it's just a straight line, right? So from 0 to 1, you can see that a of t is below the t-axis. Okay, so from 0 to 1, a of t is less than 0. And these two facts, okay, combine to make the determination that from 0 to 1, the particle is slowing down. Right? So it's slowing down. And you can see the acceleration are the tangents to the parabola. Okay, and they have negative acceleration. So you have negative acceleration with positive velocity. So you have positive velocity, but you're decelerating. Okay, and that's the indication that you're slowing down. So intuitively, that makes sense. Now, from 1 to 2, we're speeding up. Right? So this is the part that gets a little bit tricky. So on this interval, we're speeding up. And why is that? Because from 1 to 2, if you look at the velocity curve, v of t is below the x-axis, the t-axis, excuse me. V of t is less than 0, and a of t is less than 0. on this interval. Okay. Right, so we have that. So when acceleration and velocity both have the same sign, in this case negative, then we're speeding up. Okay, now from 2 to 3, what's going on with 2 to 3? So from 2 to 3, velocity is less than 0, but acceleration from 2 to 3 is above the t-axis, so acceleration is greater than 0. And when velocity and acceleration are in opposition, you're slowing down. Okay, when velocity and acceleration are in opposition of sign, you're slowing down. And then, of course, from 3 to infinity, everybody's positive and you're speeding up. Okay, so some interesting features of that. All right, what next? Okay, so now we deal with the distribution of density of a rod. Okay, we talk about the concept of linear density. So next topic, linear density of a rod. Okay, and this is particularly important in civil engineering. So if we have a rod, okay, so imagine a piece of rebar or something. All right, so let me draw a rod. So here's a rod, okay, like this. So we'll call this a rod. And, okay, so the rod has, so say if we delineate this distance right here, we'll call this distance x. And so the way the rod is physically characterized is that along this distance, this part of the rod has mass f of x. Okay, so this part of rod has mass f of x. Okay, so and let's see here. So what is so the mass varies with position. All right, so mass varies with position. All right. Now, suppose I mark 2 points along the length of the rod. I call this point x sub 1, and I call this point x sub 2. Okay? So, all right, so we have a mass function with respect to some position. So the mass of the part of the rod that lies between x sub 1 and x sub 2 okay, is given by this function, delta m. Okay, delta m. Change in mass, right? Delta means change. Change in mass, which is equal to f, the mass at x2 minus the mass at x1. Okay, so we have that. And so now we define the average density. Okay, well actually we have, so we have, okay, so where m the mass is a function of position. Okay, so this is a rod with a heterogeneous mass. The mass is not uniformly distributed. Okay, so now we've got what's called the average density of the rod. Okay, so average density. So we define average density. All right, and so that would equal to the change in mass divided by the change in position. Okay, all too familiar, right? So go back to that figure which we started off this lecture with, and you can see the resemblance. And so we know that delta M is just f of x sub 2 minus f of x sub 1 divided by x2 minus x1. Okay, so that would be your average density. Now, if we were to compute average density over smaller and smaller intervals, over smaller and smaller intervals, okay, here's what happens. Okay, then we get the linear density. Then we get linear density. Rho, which is used the Greek letter rho, which stands for linear density. And so rho is equal to the limit as delta x approaches 0 of delta m over delta x. Okay, so we can extract linear density from average density. And of course, this is by definition differential m over differential x. And I refer you to the illustration that started off this lecture. All right, so linear density is a derivative of the mass with respect to length. So let's see, for example, do I have an example? So we have average density and linear density. And let's see, I have to say, all right, so suppose, for example, we have our mass function, which say is equal to the square root of x. Okay, and x is in meters, and mass is in kilograms. This means and. This symbol means and. And mass in kilograms. All right, and so the average density of the rod. So if we go average density, which we'll call this, the average density of the rod from, say, on the interval 1 to 1.2, okay, that would equal to change in mass divided by change in x, which is equal to f of 1.2 minus f of 1 divided by 1.2 minus 1. Okay, and so that's equal to the square root of 1.2 minus 1 divided by 0.2, and so that would equal to 0.48 kilograms per meter. 0.48 kilograms per meter. Okay, so that would be your average density, the average density. Now, so what is the linear density? So let's find the linear density. So linear density at x equals 1 meter. Okay, so the computation, well, we have rho, the linear density, is equal to the change in the differential of mass divided by differential x. Okay, and so that evaluated at x equals to 1 meter. Okay, and so we know that the mass function is the square root of x, so this would equal to 1 over 2 on the square root of x, because that's just the derivative of the square root function at x equals 1. Okay, and so that's equal to 0.5 kilograms per meter. So you can see the linear density is not the same as the average density. There's a slight variation thereof. Okay. All right, so what else can we do? All right, yeah, we can talk about average currents. Okay. So let's talk about average current. Okay, and so a current exists when electric charge moves. So if we have, say, a wire, okay, and then you put a voltage on both ends of the wire, okay, and so you have electrons moving this way through the wire, okay, and so this is a current. So when you have electric charge traversing through a wire, you've got current. So so what we do is we say, all right, so we say that delta Q, uppercase Q, okay, is the net charge, net charge that passes through a cross-section of the wire okay, during a time period delta T. Okay, so let's see, let's accentuate. So here we have in red, there's your cross-section. So the amount of charge that passes through this red cross-section in a given time interval will be your current. So we have average current. Okay, so average current. Okay, that is equal to the change in charge divided by the change in time. Okay, and so at T2, okay, you may have an increase in voltage, so you'll have a charge 2 that passes through at T2, and at T1 you may have a different voltage that causes a different charge to flow through the cross-section. Okay, and so this is what you have. So this would be your average current if your voltage is fluctuating. All right, so it's average current. Now, of course, if we take delta T going to 0, we just have current. All right, so current and the symbol for current is uppercase I. And so that's just equal to the limit as delta T approaches 0 of delta Q over delta T, which, as we know, that's the differential Q over differential T. Okay. All right, so you can expect to have some equations that describe current, and then you can calculate the equations that describe average current, and from there you can compute the current. All right, so let's talk about another physics example or chemistry example now. So we can talk about chemical reactions. So how about the production of water, for instance? So let's suppose we have a chemical reaction described by a chemical formula. You mix 2 hydrogen molecules plus a water molecule, and you'll get some very hot water. Okay, you'll get 2 very hot water molecules. Okay, so we have this. All right, and so what this indicates is that we have basically, in the general sense, we've got on the left-hand side of the arrow of the chemical reaction, we've got reactants. Okay, which we delineate as A plus B, and the reactants combine under certain conditions to produce a product, C. Okay, in the general sense. So we describe the concentration of reactant A. So we have concentration. So this means this symbol is a chemical symbol for concentration of material in moles. Okay, and so 1 mole. So in chemistry, there's this quantity. 1 mole is a unit of concentration, and it's essentially equal to a count of 6.022 times 10 to the 20 times 10 to the 23 molecules. Okay, that's a lot. That's a lot of stuff. Okay, it must correspond to some physical density or under standard conditions. Okay, so we measure the concentrations, and of course the reactant concentrations are consumed and the product concentrations are produced. Okay, so let's see, where can we go with this? Okay, yeah, so the average rate of reaction, right? So suppose this reaction takes place over a certain time interval. So the reaction occurs on a given time interval. Okay, so say between T1 and T2. So what we described then is the average rate of reaction of product C. So the average rate of reaction of product C can be described by the following formula. We have the change in the concentration of product with respect to the change in time. Okay, so that would equal to the concentration of product at the ending time minus the concentration of product at the initial time divided by the time difference. Okay, so we have that. Okay, and let's see what else. Oh, there's some, and so we have what's considered to be the instantaneous rate of reaction. So instantaneous rate of reaction of course you would expect it to be a limiting situation then, right? This would be the limit as delta T goes to 0. Of your change in concentration with respect to change in time, and of course you just replace the deltas with differentials. And differential concentration over differential time. Okay. All right, so we have, and this is called the rate of reaction. Okay, we just call this the rate of reaction. Okay, and there's a relationship. Now, in a reaction, concentration of C increases, and then the concentration of the reactants decrease. And so there is a formula that we can deduce, or not so much a formula, but a relationship between the rates of reaction of the concentrations with respect to the rate of reaction of the okay, so we have a relationship between the rate of change of the reactant, or I'm sorry, the product with respect to the rate of change of the reactants, and it's this relationship. The change in concentration of the product with respect to time is equal to the negative of the change in concentration of reactant A with respect to time, and that equals to, as well, the negative of the change in concentration of reactant B with respect to time. So we have this transitive relationship. And ultimately, what this maps to is that we have the basis for a chemical formula, which is this. Okay, this is a chemical formula, not necessarily a math equation. It's a mass balance equation. Okay, so we have this, and we have a potential byproduct. Okay, all right, and so there's your chemical equation. And so that being the case, if you're given such a formula, then from here, from this formula, we'll have the following relationships. We'll have 1 over A, negative 1 over A times the change in the concentration of reactant A with respect to time. Okay, that must equal to negative 1 over B times the change in concentration of reactant B with respect to time. And of course, that must equal to 1 over C. We have to use a positive number for product because the product is increasing in quantity. So that would be 1 over C times the change in the concentration of product C with respect to time, which of course is equal to 1 over D, assuming if there is a D, another product like this. Okay, so we have this relationship. All right. So what can we do with this? Can we do an example? Yes. Let me see. Let me turn to the book and see if we can. All right, so let's do number 24, section 3.7, question 24. So in this problem, we have what? 1 molecule of the product C is formed from 1 molecule of reactant A and 1 molecule of reactant B. And so we have initial concentrations of A and B. Okay, so we have, basically, essentially we have a generalized chemical equation, A plus B yields C. Okay, and then we're given that the initial concentrations of A is equal to the initial concentration of B, which is equal to A moles per liter, lowercase a. Okay, make that clear. So this would be A moles per liter. All right, so we have this. Okay, and then when the reaction takes place, the concentration with respect to time, okay, so we have this expression, the concentration of C as a function of time. The product is given as A squared times some number K time divided by AKT plus 1. Okay, so there's the formula for the output. And then K is a constant. Okay. Okay, so by the way, this is section 3.7, number 24. Okay, so anyway, so we want to find the rate of reaction at time t. So what is the rate of reaction? So the rate of reaction is this, the differential, the change in concentration with respect to time. Okay, so all we do is we differentiate this function right here with respect to t. So since it's a quotient, we have to use the quotient rule for differentiation. So that would be, let's see, that would be the bottom function, a kt plus 1 times the derivative with respect to t of the top function, which would be a squared k, minus the top function, which is a squared kt, okay, times the derivative of the bottom function with respect to time, so that's just a k, and then divided by the bottom function squared, so that would be a kt plus 1 squared. Okay, so by the quotient rule for differentiation. And so we can clean that up a bit. Can we factor out an a squared k? Probably a squared k. Yeah, so that would be a squared k times AKT plus 1 minus AKT. Over a kt plus 1 quantity squared, okay, and then we can simplify the numerator further. So that's just equal to a squared k divided by a k2 plus 1. And I guess this would be in moles per liter second. Okay, because the concentration is in moles per liter second. Okay, so that's the rate of change, the rate of reaction. It's a rate of reaction. Okay, and then the B part is, okay, so if X is equal to the concentration of C, so let me write it down. So here's the B part. So if X is equal to concentration of product, then, okay, then we want to show that, then what? What is the question? Oh, then the changing, then, okay, so this is a tricky question. Then the change in concentration with respect to time is equal to, we want to show this equation, K times A minus X squared. All right, so how do we show this? Okay, so, okay, so show that if this, then this. Okay, so X is equal to this. So we have, so we want to show, we know we have a formula for this. Okay, so we're going to make use of this formula right here. So dx over dt, okay, we have to actually get this formula from this formula. Okay, so here's how. So let's see here. How can we best do this? A minus X. All right, so we have X is equal to the concentration of C. And do we not have that formula? Yeah, so we have the concentration of C is here. All right, so we have, from part A, we have the concentration of C is equal to, from part A squared KT over, it's a K, over A KT plus 1. All right, and that equals to X. Okay, so now K times A minus X quantity squared okay, so we just plug in this value for X into this expression right here. Okay. All right, so that would equal, why does my mouse jump like that? So that would equal to K times A. Well, let's see here. Is there an easier way of dealing with this? Well, before I do that, before I jump into that, I think there's a simpler way. Before I make such a blind substitution, why don't we go ahead and calculate A minus X first? Okay, so before I do that, let's simplify this piece. So A minus X is equal to A minus A squared KT over A KT plus 1. Okay, and so we do the subtraction, so that would leave us with A squared KT plus A minus A squared KT okay, over AKT plus 1. All right, and so we can further simplify that. So that's equal to A over AKT plus 1. Okay, that's a T right there. All right, so now, so that means that K, which is what we want, K times A minus X quantity squared. What? K times A minus X quantity squared is equal to K. So we plug in this value right there. Let's see, for the whole expression. Okay. So that equals to K times all of this, A times A divided by K times A divided by AKT plus 1, like so. Square that. Okay, and that is equal to K A squared over AKT plus 1 quantity squared. And it turns out that this expression right here is equal to the answer we got in A. What was the answer we got in A? Here's the answer we got in A. So it's the same. Okay, so this is equal to the answer in A, which is the derivative of the concentration of product with respect to time. Okay, so we have another expression. It turns out this is actually called a differential equation. Okay. All right. So, but you won't get that until much later after another calculus sequence. Okay. So let's see here. And what next? So part C. So okay. So as T approaches infinity, so here we have. Let me rewrite the concentration of product again. Okay, that's equal to A squared KT divided by AKT plus 1. Okay, and so we want to know the limit as T approaches infinity. So what is the final concentration, basically? T approaches infinity of this. Well, if we look at the expression for the concentration formula, we can see that we have leading coefficients. The order of the numerator is 1, and the order of the denominator is 1. So basically, as T approaches infinity, we're asked to find the equation of a horizontal asymptote for this. And so it's just the ratio of the leading coefficients if the orders are the same. So we just divide leading coefficients, and we're left with what? The K's cancel, so we're left with A moles per liter by definition of horizontal asymptote. Okay, so you can do that by inspection. Okay, what else? Okay, and so the next question, part D, is the limit as T approaches infinity of the rate of reaction. Okay, and we know what this is. What do we say? This would be the limit as T approaches infinity of okay, and from part A we know the rate of reaction as a function of time is this formula, A squared K divided by AKT plus 1 quantity squared. And we can tell by inspection that as T goes to infinity, the denominator gets very, very large, the numerator doesn't change, and so that would equal to 0. Okay, so the rate of reaction essentially dies off. Okay, so yeah, okay. Okay, so that's 24. What next? What do we study next? So I can't do every example in the in section 3.7. I can, well, maybe. Can I? How many more examples do we have? Let's see. We have an economics example. I'm just looking at section 3.7, the different types of problems. Oh, we don't have too many more to go. Okay, so on page 228 of the book, the textbook, example 5, they talk about compressibility of an ideal gas. I'll leave it to you to read that. It's just a rehash of current techniques. What I will do is I can attempt to say do example 6. Let's see how interesting that is. Yeah, so example 6 of the text on page 229. What we're talking about here, so this is a biology problem. Biology seems to be a growth industry these days, so let's do that. Okay, so example 6, page 229 of the text. So if we have a function n which is equal to f of t. So suppose we have this equation, n is equal to f of t, and that's the number of individuals in a population at time t. Individuals in a population at time t. Okay, so we have n. And so the change in population size between two different times. So we have delta n would be the change in the population size. From T1 to T2. Okay, so we have the average rate of growth then. Okay, well, okay, before I proceed, so we have delta n is equal to the population at T2, the final population, minus the population at T1, the initial population. Okay, so we have this. And then that brings up, of course, the all too familiar average rate. So the average rate of growth that would be delta n over delta t. So that would be f of T2 minus f of T1 divided by T2 minus T1. Okay, so that's your average rate of growth. All right, and then we have, of course, the instantaneous rate of growth. As you might expect, you take the limit, right? Instantaneous rate of growth Okay, so that would be, we call this the growth rate. And that would equal to the limit as delta t approaches 0 of delta n over delta t. Which is equal to the differential n over differential t. Okay. So, so one of the things we can examine would be, say, the population growth, the population doubling rate. So let's see what we can deal with here. So, for example, let me see here. Yeah, so in the text, suppose we have a population. Oh, great. I need a bigger desk. Let me get, so this is on page. Suppose we have a population of bacteria. All right, so next page. This book is so, it's like a 20-ton brick here, this book. Okay. So consider a population of bacteria. In a homogeneous nutrient medium. Okay. So we sample the population at certain intervals. And the population is known to double every hour. Okay. So if the initial population, so we let n sub 0 equal to the initial population. So what we want to do is we essentially want to find an equation for population growth. So we have n sub 0 is equal to the initial population okay, and so we want to find the change, the population growth rate. So we want to find this, a formula for this right here, the change in the population with respect to time, instantaneous, the growth rate. So we know it doubles every hour, so we let f be our function. So we're trying to find f. So f is, okay, so f is population at time t. Okay, so after 1 hour, the population at 1 hour is equal to twice the initial population. Okay, which in the initial population is given as n sub naught. Okay, so after 2 hours, the population is equal to twice the population at t equals 1, and so that's equal to 2 squared n sub naught. Okay, and then f sub 3, the population after 3 hours, is equal to twice the population after 2 hours, and so that's equal to 2 cubed n naught. So it doubles every hour. Okay, and so now we have a formula for the population at time t. So continuing on, we have population at time t is equal to 2 to the t times n naught. So we have an exponential function. So this is called exponential growth. So the population function then, f of t, we said was n. So population n is equal to n naught, the initial population, times 2 to the t. Okay? So the rate of growth, then we want that. So how fast is this growing? Okay, well the rate of growth is simply the change in population with respect to t. And hopefully you remember how to take the derivative of an exponential function. So this would be n naught, the initial population, times the exponential function itself, times the derivative of the exponent with respect to t, which is just 1, times the natural log of the base. Okay? All right, so for example, suppose we start off with 1,000 bacteria. Okay? So what is the rate of growth after 4 hours? Okay, and so that would be the growth rate function evaluated at t equals 4. So plugging in t equals 4, we get what? 1,000 times 2 to the 4th times the natural log of 2, which is approximately, yeah, we can just leave it like that. So you can use your calculator to compute that. All right, so example 7 in the text on page 230 talks about the flow of blood through a blood vessel. I'm not going to do that in the lecture, but I would encourage you to understand the details. It's very similar to the problems. The setup or the analysis of the problem is yet again a rate of change similar to all the other problems we've done. Let's see here. Can we do another example? Oh, okay, so how about another population growth? Let me see here. Let's pick an example, perhaps. Okay, so how about no, I guess we'll go with this. Okay, I'll leave it at that. So the next class of problems we'll deal with is let's see here. would be, so we dealt with population doubling. So we want to do an economics problem. Okay, so economics, right? So that would be my next example. Okay, so let's talk about an economics problem. This would be example 8 of the text. Okay, so so in this example, this is from economics. It's funny how man-made processes can be modeled using natural processes. And here's an example of how they are very similar. So we've got a function. Suppose C of x is equal to the total cost a company incurs in producing X units of something, of a commodity. Of a commodity. Okay, so to produce X units, it costs CX dollars. Okay, so C is a cost function. C is a cost function. Okay, and so if the producer or manufacturer increases the number of items produced, increases the number of items manufactured from X1 to X2, okay, then the additional cost of producing those items is delta C. So if you increase your production, you're going to incur an additional cost, and that would be the cost to produce X2 items minus the cost to produce X1 items. Okay, and there's a term for this. This is the average rate of change of the cost. So we have delta C over delta X. The change in cost with respect to quantity produced is C, the cost of X2, minus the cost of X1 over, okay, so we have this quantity, and this is called the average rate of change of cost. So this is the average rate of change of cost, all right? Which intuitively makes sense. Okay, so now what do we have? So as you can pretty well guess, we're going to drive delta X to 0. So what we have is before we do that, let's fashion this in terms of x sub 1. So this would be cost of x sub 1 plus a change in x sub 1 minus the cost of x sub 1. Kind of write it in a difference quotient style. This is kind of like a difference quotient now. Okay? And so we have the instantaneous rate of change of cost. Instantaneous rate of change of cost. Okay, so that would be the limit as delta x approaches 0. Of c of x1 plus delta x minus c of x sub 1 divided by delta x. Okay, so it's the limit of this difference quotient. And so we call this, of course, differential c over differential x. And this is called the marginal cost. Okay, so this is equal to the marginal. So the marginal cost is the derivative of the cost function, whereas the average rate of cost, okay, is this. The average rate of change of cost is this. So compare the two, marginal cost versus average cost, rate of change of cost. Okay, so what can we do? What can we do with this? Now, in manufacturing, of course, we often think that x would be an integer because we can only produce items in integer amounts, right? So it's customary for manufacturing to let delta x equal to 1. Okay, and so if we take a large amount of items produced, take n, suppose we produce n items, which is a large number. Okay, so we can talk about the marginal cost for n items. So what we get is we have the marginal cost of producing n items can be approximated as, okay, the cost of producing the n plus first item minus the cost of n, because delta x is 1. Okay, so this would be the marginal cost. So it's an approximation. So with that in mind, there's often an expression. The cost function is typically, in a manufacturing environment, the cost function is typically a third order polynomial, written like this: a plus bx plus cx squared plus dx cubed. Okay, so we have a cost function, typically, and a is your overhead. This is your overhead, such as rent, utilities. Okay, and what else? And these other terms, okay, and these other terms right here would be your raw materials and labor costs. Right. So, suppose we have a cost function to produce X widgets defined like this. So let's give some numbers here. Say 10,000 is our overhead plus 5X. So to produce X items, it's been determined that this is our cost function. How much it costs a manufacturer to produce X items of widgets. Okay, so that would be X 0.01 X squared. All right, so we don't have a cube term. All right, and so the marginal cost is just the derivative, and so that would equal to 5 plus 0.02x. That's your marginal. All right, and what else? So the marginal cost of 500 items. Okay, so to produce 500 items, the marginal cost would be, let's see, 500, right? Would equal to 5 plus 0.02 times 500. Okay, so that would equal to $15 per item. Okay, and let's see what else. Okay, so what this means is that if we have a production level of 500 units, all right, so if we have a production level of 500 units, then we can predict the cost of the 500 first item. Then cost of producing $500 first item, okay, can be approximately equal to this. This would equal to the cost at 501 minus the cost of 500, okay, which is equal to 10,000 plus 5, we plug this into our cost formula, plus 0.01 times 501 squared. Okay, minus the cost at 500, so that would be 10,000 plus 5 times 500 plus 0.01 times 500 squared, which is equal to $15.01. So to produce a 500 and first item will cost an additional $15.01. So C prime of 500 is approximately the same as C501 minus C500. Okay? So you're going to have to pay $15.01 more to produce 501 items over what it costs you to produce 500 items. Okay? All right. So this is the rate at which costs are increasing. Okay, so it's costing $15 more to produce an item at the 500 first level than it was at the 500 level. All right, so that's an economics problem. Now let's see here. Do we have some more questions that we can deal with. Okay, so question 32 is very similar. I want to try and do question number 6. Let's go back and revisit question 6. There was of section 3.7. So let me work that for you, and this will be the last problem we'll deal with in this section. Okay, because I think there's it's kind of a tricky WebAssign type problem. So let me pull it up. All right, so in this problem, we're given a couple of graphs. This is number 6 of the section 3.7. Two parts, so 6a and b. So we're given two position functions. All right, so here we have the illustration for problem number 6. And the question is, in number 6, we're given two position functions, and we want to know when is the particle speeding up and when is it slowing down. Okay, so now let's do A part first. So looking at this position graph as a function of time, when is it speeding up? All right, so let's assume that we have a local max at t equals 1 and a local min at t equals 3. Okay, so we know that if velocity is greater than 0, then, okay, so the velocity is greater than 0 when what? When the velocity, you do have an understanding, is the slope of the tangent line to the position function. So velocity is greater than 0 when the position function is increasing. Okay, so it's speeding up when the position function is increasing, and so we see that the position function, by definition of an increasing function, is increasing on this interval, and it's increasing. Let's see, and it's increasing on this interval, 3 to 4. So we have that. Okay, so it's slowing down when s is a decreasing function. Okay, and so that happens on the interval 1 to 3, because you can see that the slopes of the tangent lines on interval 1 to 3 are negative slopes. Okay, so it's slowing down on 1 to 3. Okay, so what else? So another aspect of this question. All right, so another way of looking at it is so it's slowing down. Oh, wait a minute, hold it. Yeah, so velocity, so we know where velocity is. Okay, so speeding up. Okay, so that's the velocity. So the velocity is, so we're not quite done with the answer to this yet. So we know, yeah, here was the tricky part of this question. A particle is speeding up. Remember at the start of this lecture, we had two criteria for speeding up. Okay, when velocity and acceleration have the same sign. So when velocity is greater than 0 and acceleration is greater than 0, okay, that's criteria 1. Velocity is less than 0 and acceleration is less than 0. Okay, so these are the two criteria for speeding up, and of course slowing down when velocity and acceleration have opposite signs. So that means it's slowing down when v is greater than 0 and a is less than 0, or when v is less than 0 and a is greater than 0. Okay, so now we know when the velocity is greater than 0, so we have this, right? Okay, and we know when the velocity is less than 0. So what about acceleration? We need to know the sign of the acceleration on these intervals. Okay, so here's the technical note. that I need to offer up. Okay, so the technical note is the sign of acceleration. We have, okay, acceleration will be greater than 0 when the position, the graph for S, is concave up. Okay, so let me give you a definition for concave up. An omission in the book, obviously. Okay, so a graph is concave up if it's shaped like this. Okay, in other words, if you pour water into the graph, it'll hold water. So clearly, the graph, in this case, our graph is concave up, say, from 2 onwards. Okay, because at t equals 2, the graph transitions from concave down. Okay, so let me tell you what concave down is. So this right here is concave up. Concave down happens when you have a graph that's shaped like this over a certain interval. Okay, when you pour water into it, the water spills out. All right, so for this particular case, we have concave down on this interval from 0 to 2. And at t equals 2, we have a change in concavity. So at t equals 2, we change from concave down to concave up. So this is a subtle point I wanted to clean up before I closed out this lecture on 3.7. So a equals 0 is concave up. A greater than 0, excuse me, A is greater than 0 when S is concave up. And for this graph in 6a, it happens on the interval 2 to 4. So that's on 2 to 4. Okay? And A is less than 0. When A is less than 0, the acceleration is negative when S is concave down. Okay? And there's a name we give for this. Okay, so there's a name we give for this point of transition from concave. When the concavity changes at a particular point, as is in the case here, this is called an inflection point. Okay, when concavity changes. And we'll study more about inflection points in chapter 4. But from a geometry standpoint, that's what it's called. So now, we need to decide where both B and A are greater than 0. And that happens at the intersections of, so we need to take the intersection of what? This is where V is greater than 0. Okay, so what, 3 to 4, 0, 1, 3 to 4. So this is the interval on which V is greater than 0. And we need to intersect that on the interval for which A is greater than 0. Okay, so we need to intersect these two regions on the t-axis, and so that happens only at 2 to 4. So right. No, I'm sorry. That would be 3 to 4, right? Those two intervals only intersect on 3 to 4. Yeah, because this interval intersected with this interval is 3 to 4. Okay. And so that's part of it. And so okay, and so this would be A greater than 0. And then we have to find out, okay, so where is B less than 0? B is less than 0 on 1 to 3, right? So we need to intersect this interval. Okay, this is where V is less than 0. And we need to intersect that where A is less than 0. So where is A less than 0? Well, A is less than 0 on 0 to 2, right? From the graph. So we need to intersect this with 0, 2. Okay, so what is the intersection of these two intervals? So that would be 1, 2, right? All right, let's see. 0 to 2. Okay, so that would be 1, 2. Okay, yeah. Well, those two intervals. Okay, so on these two intervals, B is speeding up. No, the particle is speeding up. So not B, particle, speeding up. And then since we're covering, okay, so speeding up, and then so if it's not speeding up, then we're either at rest or we're slowing down. So I'll leave it to you using these notions to figure out the interval on which it's slowing down. Okay. And then you can do the same. I'll leave it to you as an exercise to figure out where it's speeding up and slowing down for the B part. So in this case, okay, so I can tell you this right here. A is greater than 0 because it's concave up. On this part, okay, A is less than 0 because it's concave down. And then on this part, from, I guess that would be 2, this would be, so for this branch of the curve, A is greater than 0 because we're concave up. Okay, and then you can just do your, you know where V is greater than 0 and V is less than 0, okay? And so you can make the you can do the calculation. So I just wanted to introduce, take this time to introduce how you can figure out acceleration from a position curve. It just has to do with the concavity, which you identify as the concavity of the curve. For now, okay. So I believe this will conclude our discussion for section 3.7 of the text. There's a lot crammed into this section, and there's a lot crammed into the next section as well. So I'm going to have to devote an entire video lecture to section 3.8. So please, at this time, get started on your WebAssign problems and start looking at your Chapter 3 project. And let me know if you have any questions. Okay, so yeah, so that's it for now. Have a nice day.